All right, this is the last section that we're doing in chapter 10, section 10.4. Today we're going to take a look at the first half of this description, measures of central tendency. The other half of the video, and a portion of this will also be the variation, but the other video that was posted for you to watch later is all about the variation component, okay? So this one's going to cover a little bit of both. We're going to start with measures of central tendency. So central tendency has to do with how data sort of bunches up together. How is it grouped together? And in particular, there are three different types of measures of central tendency. The first one's called mean, and it is the one that you mean when you say average, right? If you're talking about your class average or the average height of a group of students, this is the one you're talking about. A mean is also called an arithmetic mean. It's found by adding the values together and dividing by how many you have. Now, when you do things like our gradebook on a point system, you divide by the total number of points and then you percentage it out. But it's the same idea. You're still doing the same process. You're dividing by how many you have. In this case, it would be how many points there were in the class. Okay, so this is the one you're most familiar with. The other two are used in different situations, though, as well, and can sometimes be more appropriate depending on the context of what's happening. So the next one is median. Median is the middle value. It is found by listing all the numbers in numerical order. If there's an odd number of values, it is the value in the middle because there will be an even number of values on either side. If there's an even number of values, what you do is you take the average, as in the mean, of the two that are in the middle. Okay, so picture having all of your kids in your classroom. A lot of you have done observations recently. And let's talk about height. Let's picture them having them stand in order of height. Shortest on one end, tallest on the other end. Can you picture that? Okay, the person that's in the middle, if there's an odd number of people, their height would be the median height. Okay? Half the people are shorter, half the people are taller. If there's two people in the middle, maybe they're the same height to begin with. That's great. Then you just have their height. But if they're slightly different, we would take their two heights, average them together, and we would get the median height that way. Okay. Median does a really good job when there's these sort of strange outliers in what you're discussing. So like, let's say, for instance, you wanted to know the average, quote unquote, salary in a specific school district. That's kind of within your realm of important things at some point in your future, right? Well, it probably doesn't really make sense to throw the principal's salary into that equation. It's an outlier, right? It's one person whose value may make everything look a little bit better than it really is. But it also might not make sense to throw in there, the student grader who comes and grades for somebody, 3 hours a week, right? So this allows outliers to not affect the actual value nearly as much, right? The next one is mode. Mode is the number or numbers, because there will be more than one, that occur most frequently. So like imagine that you were stocking shelves at Kohl's, okay? And you want to know what size of some clothing to buy. Well, what you really want to know is the number of pieces of clothing of that size that are generally purchased, right? So if everybody comes in and buys a medium, then it really doesn't matter if the average person's, size is a large. Medium is what you're going to sell the most of. So you're looking for what happens the most frequently in a context like that, and that might be a better determination for the average. Okay, the central tendency. Okay, so we're going to do an example. Our example has absolutely no context, so this is not a good example for whoever's doing 10.4. Nobody is. I don't think anybody selected 10.4. But this would not be a good example to show on a presentation day, right? Okay, so we're going to find the mean, the median, and the mode. So we'll do them in order just because they're listed that way. So the mean is found by doing what? Yes, we're going to add them all together. So I have 18, 22, 22, 17, 30, 18, and 12. So we're going to grab a calculator to add those. And we're going to divide them by what? 7, because there are 7 values. So you can either show what I've just written down as a how do I show my work step, or you can show the next step, but you have to show something. Okay, so my next step that I'm going to write down is what I would have sort of gotten out of the calculator by adding all those values on top together. What do all those values on top add to? 139. Okay, so if you show the first step or the second step, I'm good with that. But what you can't do is just show my last step. What is 139 divided by 7? And we're going to round with one decimal for what we're doing. 19.9. So you can't just jump to the 19.9. If only it were 140 over 7, that would be so much more friendly. I should probably change the problem when I rewrite the class for the new book. That's probably what I should do. Okay, never mind. Median. Okay, so median means I'm going to put them in order. You can go smallest to largest or largest to smallest. It doesn't really matter. I tend to go smallest to largest usually. So 12 would be my first value. What would happen next? 17. And then 18. Another 18. 22. 22. And 30. Okay, and you actually need to write them in order. Like that's part of finding the median. That's the showing your work stuff, right? So what value, because there's an odd number of them, there will be one specific value that's in the middle. Which one is it? 18, and specifically it's the second 18, right? Okay, I'm going to show you what it looks like when we do it the other way in just a moment, but 18. That's my median. And then mode. So mode is the number that occurs most frequently, and we actually have a couple of them here. So what numbers occur most frequently in this one?
18 and 22.
Yep, 18 and 22. And we would call this bimodal. There's two modes, but you can have more than that. You can also have no mode. No mode means every number appears the same number of times. So they all appear once, or maybe they all appear twice. But if there's any number or numbers that occur more than the rest, those are the mode. Okay, the one that occurs the most. All right, so let me just make an alternative example real quick. Same set of data, we're just going to remove, let's remove the first one. So let's start with 17, 18, 18, 22, 22, and 30. Because I want to show you what happens when there's an even set of data, because this always trips people up. Okay, so if there's an even set of data, then what that means is that this is the middle, right? Half of the values are below, half of the values are above. Everybody good with that? So we would take the two values that are in the middle, 18 and 20, and we would, 22, sorry, and we would add them together and divide by 2. This would actually give us the number 20, and 20 would be our median. Does that make sense? That's how that works. We're going to look at an example of something called a box plot in a moment, and I'm going to come back to talking about how this plays out on a box plot too. Okay, these two differences. Let's look at some other examples, though, that relate these ideas together in a more contextual sense. So this is an example of grades one. So the mean score on a set of 20 tests is 75. What is the sum of the 20 test scores? Now, I didn't exactly write this down in a formula perspective, but this is what I said. I said that our mean is the sum divided by the number of values, right? So this is our perspective, even for this problem, in a more formula point of view. They tell us this time the mean. The mean is 75, so we actually know the number that's on the left this time. It wants to know what is the sum, so that's the thing we don't know. Feel free to put a variable name there if you wish instead of the word sum. I'm just going to let it still say sum for the moment. And it says that there's 20 tests, which means that the number 20 would be the number of values on bottom. And what would I do to find the sum? Sure, you could do that. 75 over 1. And then what, Catherine? You could cross multiply, sure. So if we did this, we would have 75 times 20 is going to equal our sum. And what is 75 times 20? It is 1,500. Okay. This is how I can tell you at the beginning of the semester when I know how many points I'm going to put in my class. I'm going to put 700 points. I'm going to put 750 points. This is how I can tell you that if you need to, if you want to have an A, this is the number of points you need. It's done this way. It's exactly like this. So when you look in the syllabus and you see that part of my syllabus, that's what I did. I multiplied our total number of points times the percentage that you wanted, or the average you wanted for that grade. Okay, a little bit more involved is the next one. I might actually change this one next time too, because, like the majority of my students are female, and this probably is not always the best contextual question for everyone in the class, but we'll be okay with it. The mean weight of 7 linesmen on a team is 230 pounds. Okay. The mean weight of the 4 backfield members is 190. Their position it's irrelevant to the question, so don't get hung up on this, okay? And it wants to know what is the mean weight of the 11-person team. And here's the thing. They give us 2 values of weights, but there's not the same number of people that average together to make those weights. So we can't just say 230 plus 190 and divide it in half. Are y'all with me on that? Okay. So what we have to actually do is we kind of need to figure out how much total weight there is. So in a very real sense, we're still doing that the mean is the sum divided by the number of, in this case, their players. This is still what we're going to do, but finding the sum on top is going to work a little bit differently. So we're looking for the mean. We know how many people are on the team. It's 11. All right, so thinking about how we did this problem here, right? We took our number of values and we multiplied it by the mean. That's essentially what happened when we had the 20 and the 75, right? Number of values times our mean. We can do the same thing with our football players here. It says that there are 7 linesmen whose average is 230 pounds. So I can find their total weight by multiplying those values together, just like I did with the total number of points on the previous slide. So our 7 linesmen times 230 pounds would be the total weight if you put them all on, like one of those Biggest Loser scales, you know what I mean? Just stick them all on there and it totals out. Do y'all know what I'm talking about? Have you seen this? Okay. This is what it would look like if you stuck them all on a big giant scale. So that's those players. We have 4 other players, the backfield, and those 4 players average 190. So if they're 190 on average, then if I take 4 times 190, that would be their total weight. Okay, does that make sense? Okay. This same thing can be done with grades, by the way, if you have a grade that's worth more percentage-wise than something else. So if you're working with a percent-style grading system instead of a point-style grading system like I use, this is what you would do as well. My children's school does it like this, and so I can go in and I can tell them what they need to get on a test to get a whatever grade, whatever, and they're just wowed. They're not really, they don't care. But I know how to do that because I understand how the percents work on that. All right, so if I multiply all this out on top and then divide by 11, I'll let you do all of that at the same time if you'd like. What is the average weight? And again, we'll use 1 decimal of accuracy as we're working pretty much in this entire section, okay? 215.5. And there are units on this one, right? They're pounds, so we want to write them down. The average weight for these 11 football players is 215.5 pounds. All right, so far so good? Okay, everything we've done so far is the central tendency part. We're about to shift gears and look at some different things related to measures of variance. Okay, so measures of central tendency have to do with how the data groups itself together, right? Measures of variance have to do with describing how the data is spread apart. And both of those pieces of information are important when you're taking a look at data. Okay, so I'll remind you of a data set that I talked about once before. I talked about a data set where it was about Huntington's with my family, and I told you the average age of onset is the age that your parent had it at, okay, when they had onset symptoms. But the variance was plus or minus 18 years. It was very spread apart, okay? So variance is one of our measures of variance itself is actually one of our measures of how things vary. There's some others that are as well. So the first one we're going to look at is really simple. It's range. Now we use the word range in a couple of different contexts in mathematics, and so we want to make sure we understand what this one is. This range is just the difference between the biggest value and the smallest value. So it's very easy to calculate. It's just a subtraction, right? Find the biggest, find the smallest, subtract them. That's range. That does tell us how spread apart the data is, right? How far apart is this, right? My 18 years spreads things apart pretty big when we're talking about ages of people, right? It's not range, but still the idea is there. All right, there are different quartiles. So we have our lower, middle, and upper quartiles. Our lower, or our first quartile, is called Q1, and it is the value below which 1/4 of the data lies. So if we found that value, we could say, in whatever context, we'll do the weight one, 25% of the people weigh less than this. That's what that's telling us. Okay, it's the mark below which 25% of the people, in this case with my example with weight, would weigh. The middle quartile, or Q2, is also known as the median. We've already experienced this one, right? Median. It's the value below which 1/2 of the data lies. So again, if we were talking about weight, we would say half of the children, half of the people weigh less than this amount. That's what a median does. That's what the quartile 2, or the middle quartile, does. Our upper quartile marks the place where 75% or more, like 75% lie below. Let me say it that way. Or you can say 25% lie above. That's fine. So again, you can say, if I'm talking about weight, this is the pounds, and 75% of the people weigh less than this amount, or you could say 25% weigh more. Okay, that's what quartiles do. They split things up into groupings that are 25%. 25%, 50%, 75%, or you can look at the 75% as the 50%, or I'm sorry, 25% above, okay? We're gonna do a picture for this in a second, but I need a few more things that are gonna show up on our picture before we do it. The interquartile range is just the space between the upper and the lower quartile. Okay, that's Q1 and Q3. So it's a subtraction feature, just like range was. It's just the difference between the first and third quartile. Lower extreme is your smallest data value, and upper extreme is your largest. They're the extreme values, okay, upper and lower extreme. And we're finally to the point where we're going to put all of these things together inside of a graph, and it's called a box plot. Sometimes called a box and whisker plot, depending on the resources that you use. This can be created with the lower quartile, the median, the upper quartile, the interquartile range, and the lower and upper extremes. All of those will be present on the box plot. So we're going to use the data set. Again, it doesn't have any context. We're going to use the same data set that we saw earlier. We put it in order once before. I'm going to put it in order here again. It was 12, 17, 18, 18, 22, 22, and 30. And we identified early on that this is the median. We'll call it Q2. Okay, that's where we were from before. Q2 being the median means that I'm going to find Q1 and Q3 next. I will only use the data values that do not include the median. The median gets left out. Now, if the median wasn't included to start with, so pause for a moment while I show you this, because again, this trips people up. On my example down here where I had an even number of values, the median, 20, wasn't in the data set to start with, right? It's the smack dab in the middle thing that's sort of not present. I would still use the first 3 and the last 3 then to find the next 2 pieces, because I don't use the median, but the median wasn't there to start with. Are you with me? Okay, so let's go back to our example. So if I look at the first 3 data values, my Q1 value will be the one that's in the middle. So which one's in the middle of the first 3? 17. Okay, so this one's Q1. And what's in the middle of the last data set? Yep, 22, the second 22. So this is Q3. Usually our data sets are a little bit bigger than 7 data points. I get that, okay? And then let me change colors just for good measure. The first value is our lower extreme, and the last value is our upper extreme. And of course, all of this works if the numbers are in order. If the numbers are not in order, this is not going to work. So you've got to start by putting the numbers in order. Okay, so you're going to draw a number line, okay? Your number line needs to start at least at the lowest value you have. So ours is 12. And go up to the highest value you have. Ours is 30. So here's 12. We want to make sure things are fairly evenly spaced. Okay, so nobody's going to take a ruler and make sure you're perfect, but I do want to make sure as you're looking at it, it looks reasonable. Okay, so as I'm marking them, you can label each one. You can label every other one. I'm going to choose to label every third one. And they're all too big. So let me subdivide them and we'll mark it again. My apologies, 15. All right, that'll work. So I've gone from 12 to 30, lower one, the upper one, and they're all there. All right, so the number line is below the graph, and everything I draw is going to be elevated above it. It's not going to be touching my number line. The number line is just giving scale to my picture, okay? So we're going to draw a dot, goodness gracious, at each of the important values we identified above, the lower extreme, the Q1, the Q2, the Q3, and the upper extreme. And I'm just going to put a dot up here at about the same height across. So at 12, I have 17, I have 18, I have 22, and I have 30. Okay, just a dot to represent the location. The outer pieces that connect the lower extreme to the first values in the Q1 and Q3, you just connect them with a line segment. So they just look like this. So we've got these sort of random pieces out here. The part that's in the middle is a box. The box will have a mark, a vertical mark at the first value and the last value and the middle value. So there's a vertical bar height, if you will. I'll write them in just so you can see them really clearly. At 17, there's one at 18, and then there's one at 22. So can you see why sometimes people call this a box and whisker plot? Looks a little bit like whiskers, okay? So some resources will call it that. What this does, okay, I know our data set wasn't very big, but pretend for a moment it were a little bit bigger, is it shows you at a glance some really important values. It shows you that the median, that middle value, is at 18. You can just see it right there on the graph, yeah? It shows you how low the values go and how high the values go. It also shows you where the bulk of things are, right? The biggest pieces of the graph are the most data values, right? So there's more data values, for example, sort of lying in between, or they're more spread out, I should say it that way. They're more spread out between 18 and 22, even though there's the same number of them as there are between 17 and 18, right? So it gives you some information, but it also hides some information. You can't really see any of the individual data values. Well, not any of them, but most of them. Most of the individual data values are now hidden from view because they've been somehow grouped together with other things. There's one more thing that you need on this, and I'm going to just write it in because we don't have context. You need a title. So just write your word title. Because ours does not have context, there's no title for us to write. But in general, the ones that you do may have context, and if they do, they need a title. Okay, everybody good? Okay, so this is a graphical representation, sort of a hangover from 10.2 and 10.3 of looking at variation and measures of central tendency in a nice sort of display.
Do you have to find the IQ?
You don't have to find it, but you can see it from the graph. So the IQR on the graph is going to be the width right here. And so if you have the graph already drawn, it's easy to see what the IQR is. It's also easy to see because that's what IQR is, the middle 50%, right? 50% of the people who did this or who weighed this or took this are between 17 and 22. So it gives you the data there on there. Yeah. All right. There are two other measures of central tendency that we're going to look at quickly. The first is called mean absolute deviation. We can abbreviate it MAD if you like. It makes use of the absolute value to find the difference that each data point is away from the mean. It's found by taking all absolute value differences and averaging them together. Okay, so we're going to write that down. We're going to write down the next one, and then we're going to do them together because they're very similar. The next one is variance, which intermerges with a standard deviation. Okay, these two go together. Variance, what we do, and this is a setup on it's an algorithm. It tells you step by step what you do to get it. We find the mean. We know how to do that. We subtract the mean from each number. We square those values that we got in step 2. We find the sum of them, i.e. we add them together. And then finally we divide by the number of values. Once we've gone through all of that, we find the variance. The reality is variance isn't really used for very much. It's the final step, standard deviation, that we find. Standard deviation is sort of like step number 6 in this process. You square root the variance. That gives you the standard deviation. Okay, it gives you the standard deviation. And standard deviation is what is used in the video that's posted for you to watch later. The mean and the standard deviation are crucial when we're looking at what are called normal distributions. Okay, so let's actually find these for a data set, our favorite data set, the only one we've used today, right? All right, so we have the same values we had before. We already found the mean, so we've already done step 1, if you will. One of the ways that you can write mean is with an X with a bar on the top. That's a pretty common one. There's some others, but we're going to go with that one. And we found that mean to be 19.9. Okay, so that's step 1 in this list of steps. Step 2 says I'm going to take each of the values that I was given. Oh, this is mean absolute deviation. That's okay. We're not ready for our steps. But here's our X values. I'm going to list them out over here in a chart. So I'm just going to list them in the order they were given. So 18, 22, feel free to use a different order if you want. 22, 17, 30, 18, and 12. And this right here is going to be these X values subtracting the mean. And I want the absolute value. In other words, I really don't care if it's positive or negative. Okay, so ignore the sign. So if I take 18 and I subtract 19.9, I'm going to get 1.9 if I ignore the sign. And if I do 22 minus the 19.9, I'm going to get 2.1 if I ignore the sign. Does everybody understand what I'm doing to get these values? I'm just subtracting that 19.9 for each of them. Some of these repeat, so I have another 2.1. 17 gives me 2.9. 30 is the most interesting because it's furthest away. It actually gives me 10.1. 18, I'm back to 1.9. And on 12, I'm at 7.9. So when we're doing mean absolute deviation, we calculate all of the absolute values and we add them together. So in an effort to make sure we get finished in time, I'm just going to tell you what the values are. Are you guys okay with that? Right. So this is 28.9 if I add them up. And if I want the mean absolute deviation, what I do then is I take the 28.9 and I divide by my number of values, which is 7. This is 4.1. That's probably a rounded value because we continue to use 1 decimal here, so it is approximately 4.1. Okay, telling you how far things are spread apart, which makes sense because we're taking each of the values and we're taking it away from the mean, which is the central value, right? Okay, standard deviation for this one then is almost the same. Okay, we're doing variance first and then standard deviation. So our chart looks much the same. we had the same mean, right? Its x bar is 19.9. We have our values in order: 18, 22, 22, 17, 30, 18, and 12. And our first column after that is the same thing that we just did before. It's really just the absolute value of x minus x bar, and we already did that, right? We don't need to calculate those again. We already did them. They're 1.9, 2.1s, 2.9, 10.1, 1.9, and 7.9. Okay, so that's steps 1 and 2. Now, I know step 2 actually just says to subtract it, and it doesn't really say you can do the absolute value, but you can, because what's step 3 say you're going to do? Feel free to turn back. What did step 3 say you're going to do?
Square the difference.
You're going to square the difference. And Sydney, what happens when we square a negative number? It turns positive. So it doesn't matter if any of the values that I just wrote down could have been written negative, right? I'm going to square them anyway. So I might as well ignore the negatives when I don't need to worry about them anyway. So we're going to take the x minus x bar, and we're going to square them. Again, to avoid you having to type all these in, let me just tell you what they are. It's 3.61, 4.41, 8.41, 102.01. That one's a big one. I'm off now. No, I'm not. I just didn't write my 4.41 down twice. I'm sorry. There was 2 of those. And then I have 3.61 and 62.41. Okay, so that's step 3. So this was step 1. We'll label them. This is step 2. This is step 3. Step 4 down here is finding the sum. Okay? So the sum here is 188.87. 5 says that we're going to find the variance. And I do that by taking that 188.87 and dividing it by the number of values, 7. With 1 decimal, this gives me 27.0. That's variance. But variance doesn't really give us a lot of information. It's the standard deviation, which is step C, that tells us something. Finding the standard deviation, so this is it, but I'll flip back, okay, so in case you're still writing. So part C here, standard deviation, which is sort of like step 6, it just takes the square root of step 5. So the square root of 27 is about 5.2. And that's the standard deviation for our problem. Okay? Notice it's not significantly different. It is different. Usually it is different, but it's not significantly different, 4.1 to 5.2. When you get to the next video, you're going to be taking a look at normal distribution, and all of those standard deviations and means are going to join together to describe to you what they're used for. All right?